So hello friends, welcome back to my channel. So first of all, first things first, I was unable to give up a question on the technique of transferring the segments. So here is the question. You can think of this question as an assignment to the previous concept, the concept I taught in the video before 1 week, exactly 1 week before. So this question is from South Africa 2006. And this says in triangle ABC, AB equals AC, angle BAC equals 100 degree, and D is a point on AC such that angle ABD equals angle CBD. Now you got to prove that AD plus DB equals BC. It is a very elegant application of transferring the segments. All can try this off. Now today we are going to learn some concepts, and in the end of the video I'm going to leave you with 10 problems, competition level problems, where you can apply these concepts on. So first of all, these concepts are very simple, but they have very elegant application. First of all, the concepts are regarding the perfect squares. So perfect squares, and the second will be on factoring trick on Diophantine equation. Now, perfect squares. So there are some properties of perfect squares. What are they? Let's start with the first property. Any perfect square, let's say a natural numbers perfect square, always leaves a remainder of 0 or 1 when divided by 3, 4, and 2 respectively. I mean, if any of these numbers divide this and square, they always leave a remainder of either 0 or 1. You can easily comprehend that when the number is, in case of 4 and 2, the even it leaves remainder 2, and when it is odd, it leaves remainder 3, and in case of 3, we can't exactly say anything surely. Similarly, n square is congruent to this. Congruency just means that when, for example, if there were only 3, so any square leaves remainder of 0 or 1 when divided by 3. Similarly, any perfect square leave a remainder of 0, 1, or 4 when divided by 8. And similarly, you can test all numbers. For all numbers have got a very elegant application. This modular arithmetic itself has very elegant applications and Olympiad style problems. Now, what I want you to know is the last digit. So, taking mod 10, I mean the last digit of any perfect square, these are the only possibilities. 6, 9, 0, 1, 4, 5, 6, 9. No number can end with any digit except these. I mean mod 10. So the concept I want you all to focus on is the second last digit. For example, the number will leave the last digit as 1, 5, or 9 when it is odd, clearly, because these numbers are odd. So the second last digit, for example, if I ask you that any number ends with 9, as any number which is a perfect square ends with 9, what is the second last digit? Is it even or is it odd? So the answer will always be even in case of 9, 5, 1, or any odd number, which is a modulo 10 of a perfect square. And there are only 3 possibilities, 1, 5, and 9. So why does this happen? So by Euclid lemma, we can write any number in the form of 10k plus minus of 1, so that the unit digit is 1, or 1, I mean the square n square ends in 1. We can write any number as in this form to 10k plus minus of 3, I mean 10k plus 7 or 10k plus 3, here 10k plus 9 or 10k plus 1, and simply 10k plus 5. because plus minus don't matter here. 5 is equidistant from 10. So what happens is when we square these, so if it is a 1, so the last digit would be 0 and 0 would be carried to this number 100k square, 100k square minus 20k plus of 0 1. Now this is even, and when even adds to it, the last number obtained will also be even. That is by simple logic. Similarly, if that was 81, I mean there was 10k plus 9 or minus 10k minus 1. Again, this 8, an even number, will be carried to some even number, which again results in some even number. Similarly here, so either this will be 0 9, and this will be carried to this number, which is even, again even, or it will be 10k plus 7, that is 49. This 4 would be carried to this number, which is even, again even. Similarly 25, any square ending in 5 with square root as ending in 5 has a special properties, always ends in 25, whatever be. Again this 2 is carried to this even number, and which again results in even number. So this was the concept we we will use, you are going to use in the the problems I leave in the end. Now one more property, that is any number that ends in 6 always leaves the last second digit, and always has the last second digit as an odd number. Why so? So then there are only two possibilities you can imagine, that is 10k plus minus 4. That means this is so that the last digit squares. I mean this, yeah. So there are only two possibilities for the number square to end in 6. That means the number should be either in the form of 10k plus 4 or 10k plus 6. I combined both and wrote 10k plus minus of 4. So what do I mean is, why does this happen? So again, this number results as 100k square plus minus 20k, and this is plus 16. Now this is an even number. Now this 1 when gets carried to this even number, that results in an odd number. So, or if that was 10k plus 6, again this 3, an odd number, gets carried to this even number, and which again results in an odd number. So that's why any numbers square, if mean the square root has 4 or 6 as the last digit, that number second last digit would have square of that number second last digit would always end in odd number. It is evident that 16 square equals 256. Second last digit is odd. 26 square equals 676. Second digit is odd. Let's move lower. 6 square 36. Second digit odd. 36 square 1296. Second digit again odd. And similarly, we can prove our claim in this. So these were the important facts that we needed to deal with the problem. One of the parts which we need to deal with the problems. So yeah, let me cut this thing off. So yeah, this is the problem. Let's shift this upwards. Now this is the problem that states as prove that any positive integer n greater than equal to 10 cannot be a perfect square if it is found by the same digits. What does this question mean? That means this says that 1 1 1 1 1 1 1 1 n times can never be a perfect square, or 2 2 2 2 2 2 2 2 2 and so on can never be a perfect square. Similarly, up to 9 9 9 9 9, this can never be a perfect square. This is the very elegant application of what we just learned. So let's begin. Assume this case first, 1 1 1 1. Now, since we learned that any number ending in uh, an odd digit, you can first of all I want you all to try this problem yourself. This is a very elegant application if you know the concept. So let's begin with the solution. Now we learned that any number ending in an odd number 1, 5, or 9 must have the second last digit or as even. So this has an odd digit, so this can never be perfect square. Since this number right here can be written as 2 times 1, 1, 1, 1, 1, 1, and neither of this and neither of this is a perfect square, so the number itself is not a perfect square. Same is in the case of 3. 3 has a usual property. I hope you can recall it. I explained it. Any perfect square can never end in 3, or you can think of it as also as like the second last digit is odd. So, but the better would be to think that no square can end in 3. So this can't be a perfect square. Similarly, on 4 can be written in this manner. Whereas while this is a perfect square, this isn't. So the number itself isn't a perfect square. 555, you always know any number with the unit digit is 5 ends in 25, or we can say this number right here should be even. But in this case, this is 55555. So this can't be a perfect square again. Similarly, 666, the second last digit should be odd. As I told, any number ending in 6 must have the last digit is odd. Again, this is not possible. This because this is even. 7, 7, any perfect square can never end in 7. So again, this cancels. 8, no perfect square can end in 8, not possible. So, and the last one is 9. 9 can be written, and the second last digit is odd, but it should be even. So impossible. Now, since 000 is not greater than 10, we cannot assume that to be a part of this question. So that's how that those properties come into use and will come into use in the questions I will leave at the end. So the second question second concept rather we are going to learn is on the factoring trick in Diophantine equation. So a Diophantine equation is an equation which has solutions in integers. They might be very specific, very strict. That is, they might be bound in positive integers, might be bound in only throughout the whole integers. Factoring trick in Diophantine equation. Diophantine equation. Now some people also call it SSFT. SSFT stands for wait. Simon's favorite factorizing trick, SSFT. I hope you got it. So you can call whatever it want. Thing is, you should just know what it is. So let's start with a problem. Now this is a very simple problem, not from any competition or anyway. Now this is a problem. It says that mn are positive integers. Positive integers. That means they belong to I plus subset, and we got to find all possible m and n. So how do we go about it? Now the trick is to factorize this expression, because we can't always put values and check. So the trick was to add 1 to both sides. So what happens when we add 1 to both sides is this becomes 5, and we can take 1 out of here and plus of 1 from here to get 5, and thus factorize this in m plus 1 times n plus 1 equals 5. We can always find values of n such that how Remember, I have said about positive integers. So this excludes any m or n to be zero. I mean, if we say in Indian terms, that is mn belongs to naturals. So it can be written as 5 into 1 or 1 into 5. So both of these gives 1 of m and n, as because m plus 1 either equals 5 or 1, depending upon either n plus 1 is 5 or 1. So if this was the case, m would be 4 and n would be 0. So not possible. Again, if this would have been the case, m would be 0 and n would be 4, not possible. So we can clearly say there are 0 solutions in total. So this equation has 0 solution. That means no solution. So these were the two tricks I taught you, and I want you all to practice these tricks on the problems that will follow. So